Hello. Welcome to my channel. In the previous video we have introduced the hyperbola, starting from the definition. Then we have seen the elements of the hyperbola, like the branches, the axes of symmetry, transverse axis and conjugate axis, the center of symmetry, the vertices and the foci. The segment that joins the two vertices is called transverse semiaxis. We have calculated that the constant k equals 2a, the length of the transverse semiaxis. In the first video we focused on hyperbolas, with transverse axis that coincide with the x-axis, like the hyperbola in figure, or is parallel to the x-axis. Eventually we have derived the equation for these kind of hyperbolas. Firstly, in the case of axes of symmetry coinciding with the Cartesian axes, and then with axes parallel to the Cartesian axes. Now we want to analyze the hyperbolas with transverse axis coinciding with the y-axis, or parallel to it. This means that the axis that intersects the hyperbola is the y-axis or a line parallel to it. Let's start from the case of transverse axis, coinciding with the y-axis. Like the hyperbola in figure, the two vertices lie on the y-axis, and they are still symmetric with respect to the center. So they have coordinates 0, -b, and 0, b. We choose to call b the value of the ordinates, but we could choose to call it a. Eventually we would have gotten an equation with a and b swapped. So in our case, the length of the transverse semiaxis is 2b, and even the foci lie on the transverse axis, and they have coordinates 0, -c, and 0, c. Even in this case, the constant k that appears in the definition of the hyperbola is equal to the length of the transverse semiaxis. In fact, if we apply the definition to the vertex v2, we get absolute value of v2f1 minus v2f2 equals absolute value of 2b. That is 2b. Let's consider a point of the hyperbola of coordinates x and y. We calculate the two distances pf1 and pf2. Pf1 is equal to square root of x squared plus y plus c squared, while pf2 is equal to square root of x squared plus y minus c squared. Therefore the absolute value of the difference between these two quantities is equal to 2 times b. At this point, the situation is analog to the one we have faced in the first video, when the first square root is greater than or equal to the second. We can remove the absolute value without changes. Otherwise, we have to change the sign of the quantity before removing the absolute value. The first case occurs when y is greater than or equal to 0, while the second for y lesser than 0. It's exactly the same situation we have seen in the first video. For hyperbolas with transverse axis coinciding with the x-axis. Except that now we have x and y swapped, and b in place of a. Let's see how the equation changes. In this case, we derive the equation for y lesser than 0. But you can do it for y greater than or equal to 0. And you'll find the same equation. So y lesser than 0 implies that we have to change the sign of the quantity within the absolute value. Therefore square root of x squared plus y minus c squared minus square root of x squared plus y plus c squared equals 2b. We bring one square root to the other side. Then we square both members of the equation. We solve the binomial squares. Some terms cancel each other out, and by other simple calculations we get minus cy minus b squared equals b times square root of x squared plus y plus c squared. Again we square both members of the equation, obtaining c squared y squared plus b to the fourth plus 2cb squared times y. equals b squared times x squared plus y plus c squared. We solve the binomial squares. Then we gather the y squared terms, the x squared terms and the constant terms eventually. We have c squared minus b squared times y squared minus b squared times x squared minus b squared times c squared minus b squared equals 0. We notice that appears 2 times the term c squared minus b squared. If we draw a circle of radius c, and we consider a point Q belonging to the circle, of abscissa A and ordinate B, the same ordinate of the vertex V2, then we can see that the triangle CQV2 is a right triangle, whose legs measures A and B, and the hypotenuse CQ is equal to C, the radius of the circle. Therefore holds a squared plus b squared equals c squared, and c squared minus b squared equals a squared. So our equation is a squared times y squared minus b squared times x squared minus b squared times a squared equals 0. We can divide each member of the equation by a squared times b squared. Because either a and b are not equal to 0, we get y squared over b squared minus x squared over a squared minus 1 equals 0. We can change the signs of the two members of the equation. Then we bring the constant term to the other side, obtaining x squared over a squared minus y squared over b squared equals minus 1. Therefore we have found out that the equation of an hyperbola, with transverse axis coinciding with the y-axis, is very similar to the equation of an hyperbola with transverse axis coinciding with the x-axis. The only difference is the sign of the constant term. That in this case is minus 1, while in that case was plus 1. If we want to find the equation of an hyperbola with transverse axis parallel to the y-axis, like the hyperbola in figure, the procedure is analog to the one we have seen in the first video. So it is the result. If we call xc and yc the coordinate of the center, the point where the two axes of symmetry meet, the equation is x minus xc squared over a squared minus yc squared over b squared equals minus 1. Well, this video is over. If you like my videos, you can subscribe to the channel. See you soon with another video. Bye.